Okay, so Bohr was trying to identify the positions of the electrons on the atom. He wanted to know where are those electrons, and he did that through spectroscopy. Okay, and he started to understand that electrons are organized into energy levels. They're organized in energy levels. Okay, so those energy levels are represented on the periodic table where? Anybody? The energy levels of the atom are represented on the periodic table where?
The columns. I mean, the periods.
Okay. Yes. So 1, 2, 3, 4, 5, 6, 7. Period 1, period 2, period 3. Those are representing the different energy levels that the atom can have, right? So hydrogen is in the first energy level 1. So if I was drawing the Bohr atom model, okay, the first energy level I would draw as a ring around that nucleus. That's the nucleus, and here is one electron. That's hydrogen. That's hydrogen's electron. Helium's electron would also be in the first energy level, but it would be paired with hydrogen. Okay? So that's the first energy level. Then we move to the second energy level. In the second energy level, I now have lithium and beryllium. Those guys pair. Why? Why do lithium and beryllium pair? They're in the same group. Excellent. Because they're in the same group. Does boron pair with lithium and beryllium? No, because it is in a different group. Who does boron pair with? These guys. They form pairs of electrons, right? They're in a different group, and so they will pair with each other. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Who do they pair with? They're in a different group. They pair with each other. How many pairs of electrons will I have from these guys? 5. There's 10 elements. I will have 5 pairs. How many pairs will I have here? 3. And 1 pair there. Okay? So the S electrons always have 1 pair. The P electrons always have 3 pairs. D electrons in the middle will always have 5. And these guys down here have 7 because they have 14. Now you're counting down here saying, wait, that's 15. Well, these two go up here, okay, these first ones. And then you get to these 14. Those are the Fs. That's the F, okay? So, S, P, D, F, we have 1 pair, 3 pairs, 5 pairs, 7 pairs. That's how they pair. And they will pair with electrons of their same group. Okay? But they don't pair until you first fill all of those available spots. So there's 3 available spots here. I fill 1, 2, 3, and then I pair. They will pair after they fill the available spots. Those available spots are called orbitals. The P subenergy level has 3 orbitals. Electrons can fill in those orbitals. And they won't pair until all 3 orbitals are filled. Once all 3 orbitals are filled, then they will come back and pair with each other. Okay? The S has 1 orbital. The D has 5 orbitals. Those orbitals will all fill first. So 1 electron in each orbital, and then they will come back and they will pair. Okay? They will pair in there. But in a simplified matter, we're just showing, okay, here's S, and then I'm moving from beryllium to boron, and I have p electrons, 1, 2, 3 individual ones, 4, 5, 6 pairs. And how many valence electrons do I have when I get here to neon? 8. And like I said, that's the magic number. 8 is the magic number. All elements, most anyways, not all, because hydrogen and helium are exceptions to that. Most all elements want 8 electrons, because 8 means stability. And if you have 8 electrons and you're stable, then you're non-reactive. Neon is a non-reactive element. It's inert. Argon, non-reactive. These are called the noble gases because they're the nobility of the periodic table. They're non-reactive elements. They have reached the state that they want to be at. So they don't need to react with things because they're already stable. Reactions occur when you have unstable molecules that are trying to reach that stability. Okay? So here I am, neon. I move to sodium and magnesium. I add a third ring, third energy level. The s electrons are going to pair. They are pair. We jump to the p electrons. I'm going to have 3 individual electrons. And when I get to phosphorus, how many valence electrons do I have? 5. I have 5 valence electrons. How many unpaired electrons do I have? 3. I don't like that. On phosphorus, I do not like the fact that I have 3 unpaired electrons. So what am I going to try to do to gain stability? What's that?
Gain 3.
Gain 3 electrons. That's one way I could do it. I could gain 3 electrons, and I can satisfy that octet in 2 different ways. I can either gain exactly 3 electrons. Well, where do they come from? They come from something else. Well, who is going to give them to me?
Right.
Well, something that doesn't want to gain electrons, something that wants to get rid of electrons.
So,
Considering what we've looked at here, who wants to get rid of electrons?
aluminum.
Al does. That's true. Okay? Al does. Or anything, see this red line? Anything on that side of that red line wants to get rid of electrons because they are metals. Metals lose electrons. Copper, nickel, silver, gold, magnesium, calcium, potassium, strontium, rubidium, sodium, lithium. Those are all metals. They're all metals. They are classified as metals because they lose electrons. They want to lose electrons. How many valence electrons does potassium number 19 have?
1.
1 valence electron. How many does it want?
Unless it lose 1.
Okay, why?
Because it's easier to have resistance.
Yeah, because it wants 8, right? Look how far it would have to go to gain 8 electrons. But what if it just loses a single valence electron? Where does it go now? It had 19 electrons. Now how many does it have?
That makes argon.
18. Did it get where it wants to be? Yes. It's there. Potassium is now the same electron configuration as argon. It got there. And it just had to lose an electron to do that. And now it's stable. Okay? So potassium loses an electron. Well, who's going to take that? Who's going to pick up that electron?
Chloride.
Chloride could, because it's also deficient in an electron, and it could pick it up. And then you could form potassium chloride. Well, here we have phosphorus. If you have potassium and phosphorus and you react them together, phosphorus is deficient in how many electrons? Well, one potassium would give it 1 electron. A second potassium would give it 2, and a third potassium would give it 3. So, potassium phosphide would be K3P. I would need 3 potassiums, 1 phosphorus to create this compound. Okay, that's the ratio of potassiums. Yikes. It started writing on me. That's the ratio. Doesn't usually do that. Usually the keyboard turns off. Okay. Okay, that's the ratio of K and P, K3P, okay? All right, so let's just say we're now at argon, okay? We'll keep going. Okay, I add potassium, calcium. As my S electrons, they pair. They're in the same group, they pair. But now I'm at number 21, scandium. Now, these electrons never go on the outside. They are not outside electrons. Only this group, the S and the P, are outside electrons. Okay? So I always get to 8 on the outside when I get here. These ones go inside. They're inside electrons. So when I get to scandium number 21, where does that electron go? It goes, this is 1, 2, 3, 4. I'm on the 4th. It goes back to the 3rd energy level. Because the 3rd energy level is not full. We just added the 4s before we added the 3d. Because those are D and they're in the 3d. Okay? So they fall inside of that 4th energy shell. And we come in here and we add, there's 5 orbitals in the D. Those d orbitals do not get filled until I fill the 4s first. And then I will start to place electrons in the 3d. So 1, 2, 3, 4, 5 unpaired orbitals. And then they come back and they pair 6, 7, 8, 9, 10 electrons. Now the 3rd energy level is full. There is 18 electrons on the 3rd energy level. Okay, it is full. I have how many valence electrons here? 2. So essentially when I'm going through these elements, my valence electrons are 2. Okay, with a few exceptions that you guys don't need to learn. Okay, but that's essentially how many valence electrons I have for these guys. Because they're inside electrons, and these are their valence electrons. They fall inside. And then when I get here, number 31, I start adding where? Again. That's right, back to the 4th. Now I'm in the 4p. I have 3 orbitals in the 4p. 1, 2, 3, 4, 5, 6. Okay? Now, once again, I have how many valence electrons when I get to krypton number 36? 8. And that's how many I will always have. I will always have 8 valence electrons. That's stability. That equals stability. And that's where people want to get. They want to get to that stability. Okay? All right. So let's go ahead and, let's see here. We're going to look at the periodic table, okay? And kind of see how it's designed and the different parts of it, which we've already identified most of it, okay? So here you see all the blue. Remember what I said about the blue? The blue is what? Metals. The periodic table is mostly made up of metals. This is all metals. What is the definition of a metal? Metals tend to lose what? Electrons. Electrons. Because metals have very few valence electrons. So starting there, they have 2. And going all through this, they have how many valence electrons? 2. Well, these guys are inside of this. And so also they would have those 2. Now over here, it gets to be a little trickier because now you don't only have 2 valence, you have 3, 4, 5, 6. Why am I still losing electrons? Because of the size of your atom and such, okay? So that's a little different. But for the most part, metals lose electrons because they have very few valence electrons, okay? Those are the metals. The yellow here is the nonmetals. So if metals lose electrons, what do you think nonmetals do? They gain electrons. That's right. Metals lose, nonmetals gain. That works out really well because if you have something that's positively charged and something that's negatively charged, they can attract. And you create compounds. Okay, that's how you can begin to identify, oh, this is how chemistry works. These guys want electrons. These guys want to get rid of electrons. So if this guy gives his electrons to this guy, they can form a compound. A stable compound. And that's what they do. That's what they do. They pass their electrons to the other person and they stabilize themselves. Okay? Okay, so we've already seen this. The periods, 1, 2, 3, 4, 5, 6, 7, those are the energy levels. Okay? The groups of a periodic table called families are the columns. So like these guys, they're a group because they have similar chemistry and reactivities, which for these guys is basically none because they're the noble gases. These guys are a family. They're called the halogens. How many valence electrons do they have? They need 1 more, which means they have how many? 7. How many do these guys have? 6. 5. 4. 3. How many?
3.
2. How many? 2. 1. Okay? That's the valence electrons of the periodic table. I don't count valence electrons for the middle guys. Their valence electrons are these valence electrons on the end. Okay? So, look at the number on the top. It's going to tell you the number of valence electrons of your element. Well, why is that such a big deal? Because that's what determines what you're going to do. That's what determines and helps you predict whether you're going to lose electrons and how many you will lose, or whether you will gain electrons and how many you will gain. Because if I am nitrogen, I am a nonmetal. Nonmetals do what? Gain electrons. How many electrons is nitrogen going to gain?
3.
1, 2, 3. That's how many it will gain. Okay? And once I gain that many, I am now stabilizing myself. Right? So families have similar reactivities because they're valence electrons. And so that's how they're grouped on the periodic table. Okay. Okay, metals. Definition of a metal: elements that tend to lose electrons during chemical change. Nonmetals: elements that tend to gain electrons during chemical change. Metalloids have properties intermediate between metals and nonmetals. So we see on this periodic table the green right here. See the green? Those are the metalloids. Metalloids, and honestly, I would consider carbon a metalloid because it can have properties similar to metals. Metals conduct electricity, right? Carbon conducts electricity. So, and it has a lot of similar characteristics. So, you know, it's kind of, and it can be either positive or negative. It can go +4 or -4. And so, in a way, I would consider that to be a metalloid as well. It's kind of right there in the middle, all right, between the two groups. Okay, so metals, they conduct heat and electricity. They're highly malleable, which means that you can displace the metal atoms easily. So if I take a piece of metal and I hit it with a hammer, you'll dent it, right? You've displaced the atoms and reshaped it. So it's malleable. And ductile, you can pull it into strands like wire. You can make it into wire. Okay? It has luster. It's usually solid at room temperature, except for mercury, number 80. It's a liquid at room temperature. Kind of the exception to that. Nonmetals, they're more brittle. They're more powdery solids or gases. A lot of times they're gases because they're. We'll talk about why later. So they're kind of the opposite of metals. Opposites attract, right? So that's how they come together and form compounds. Okay, so what is all this stuff on the periodic table? Well, we can see on the periodic table here, number 14, we see these masses. So those are the masses. The 14 is the atomic number. You know that, right? We already talked about isotopes. So we're okay with that. Okay. The atomic number is the number of protons. Your charge would be dependent on the number of electrons you have. Okay, so identify the group and period to which each of the following belongs. Phosphorus. What is its group? 5A. What is its period? 3. Chromium. Let's see. That's 6. That's confusing, right? Because we don't want to confuse you with those. The Roman numeral 6A there and this one. What's this guy have? Periodic tables are all different all the time. They have different numbering ways. Oh, this is the B. They have this section B. See, they had this labeled B. They have this labeled A. Maybe we could consider this to be more like 6B. So anyways, you would run into that. But that's the idea. So going down the periodic table, that's where you find its family. The group, but chromium's group is what? I'm sorry, not group, period. 4. It's in the 4th period of the periodic table. Okay? Good. Okay. So let's talk a little bit about electron configuration. And we've already got a really good start onto how to write electron configurations. Okay? Electron configurations describe the arrangement of electrons in an atom. Valence electrons are those outermost electrons. We already know that. We're good. So you guys are well on your way to writing these. So Bohr, he's the one that has these Bohr atom models, right? And so they're identifying the locations of the electrons on the atom. And the principal energy levels, we would say, are n equals 1, 2, 3, 4. Those are the 1, 2, 3, 4, 5, 6, 7 of the periods. Okay? And each energy level has one or more sublevels, S, P, D, F. We've already identified those on the periodic table. This first one is what? S. This one? P. Good. Those are the SPDFs of the periodic table. And all you have to do to write an electron configuration is read your periodic table. It will tell you where the electrons go. Okay? Titanium is in which subgroup? D. What is its principal energy level? Not 4. Remember, 4, these two are in fourth on the outside. Where do these guys go?
So they're
3. So this guy's principal energy level is 3, and its sub-energy level is D. Its position in the 3D is number 2. So we would say titanium resides at 3D 2. Where does nickel reside?
nickel is in the D sub-energy level. That's a 3.
3D
Shell.
8. Good. 3D 8. 1, 2, 3, 4, 5, 6, 7, 8. And I get to nickel. Okay? Where does palladium reside? Well, if this is 3D, what's this? 4D 8. Platinum? 5D 8. 5D 8. Okay? Phosphorus?
Phosphorus is P.
3P 3. 1, 2, 3. 3P 1, 2, 3. Phosphorus is 3P3. That's its location on the periodic table. Okay? How about selenium?
4P4.
4P4. Excellent. Okay? That's how I'm going to identify their location. And writing the electron configuration to get there will be the same because I always start with at hydrogen when I write an electron configuration. But I just have to identify the location of that element at the end of my electron configuration. Okay? All right, so each sublevel contains one or more atomic orbitals. Energy level 1, 2, 3, 4. Energy level 4 has how many sub-energy levels? The answer to that is the number that it is. If its energy level if its principal energy level 1, it has how many sub-energy levels? 1. It has 1 S. That's all it has. It has an S sub-energy level. Principal energy level 2 has how many sub-energy levels? 2, S, and P. Principal energy level 3 has 3, which are SPD. Principal energy level 4 has 4, which is... So what do you think about principal energy level 5? How many sub-energy levels does it have? Okay, that's a good theory. But it's not quite... It has 5. It's going to follow the same thing. It's just expanded. It's gotten bigger. Every time you add an energy level, it gets bigger and bigger and bigger. And it will have a sub-energy level G. S, P, D, F, G, which we don't see on the periodic table, so we don't worry about. Okay? Don't worry about it. So how many electrons does an S sub-energy level hold? 2. How many electrons does a P sub-energy level hold? Oh, not 8.
5.
Close. 6. Right? 1, 2, 3, 4, 5, 6. The P holds 6 electrons. How many electrons does a D sub-energy level hold? 10. How many electrons does F hold? And don't count that one unless you subtract 1. 14. Okay? Holds 14. So, if you were asked the question, how many total electrons can the first principal energy level hold, what would you say? 2. The second? 8. The third? 18. The fourth? 32. Okay? That's how many electrons each of those can hold. And it's simply understood by its principal, or sorry, by its sub-energy levels. How many sub-energy levels does it have? And we know how many electrons those sub-energy levels can hold. You add all those together. That's how many total electrons that energy level can hold overall. Okay? 2, 8, 18, and 32, 1, 2, 3, 4, SPDF. Okay? Okay. All right, so that's just going to go through what we just said. N equals 1, 1 sub-energy level. N equals 2, 2 sub-energy levels. All right? N equals 1, 2. Okay, this is the formula if you wanted to know. So like for the fifth sub-energy level, we didn't get to G, but if you wanted to know how many it could hold, and you're not going to ever have to do this, but if you wanted to know, you just put a 5 there. Okay? 5 times 5, 25 times 2, 50. It could hold a total of 50 electrons. Okay? So that's how you would perform that. All right? So like here, 9 times 2 is 18 for the third. It can hold 18. All right? That's just a formula you could use. But instead of using the formula, what I really want you to understand is why. Why can it hold 18? Because it has an S, a P, and a D. And the S holds 2, the P holds 6, and the D holds 10. Okay? So if you understand that, you'll be better off. All right. So how do these relate by energy? Well, an S sub-energy level has lower energy than a P, which has lower energy than a D, which has lower energy than an F. And electrons fill by energy. They go to where it requires less energy. That's what we do, right? We're going to climb a mountain. We usually go the easy way, the way that's easiest, right? We go to the way that requires the least amount of energy. But so electrons do the same thing. Whichever gives the least pushback, that's where they're going. Okay? So it's easier to fill into the S than the P, than it is to the D, than it is to the F. So that's how I'm going to fill. But we saw a little bit of an exception to that after we got here. We said P, S, then D. Okay? That's because those S, the 4S, is lower in energy than the 3D. It's easier to put those electrons on the outside in the S than it is to shove them into that third energy level, which already has electrons in it, push them in there into that D sub-energy level. And so they're following that same idea. They're going to fill according to where the least amount of energy is. The 4S is lower in energy than the 3D. And so they will fill there first. Okay, SP, SPD, SPDF. Okay, 1, 2, 3, 4. All right, so this is kind of the idea of how these orbitals look. An S is a spherical orbital. P kind of has this dumbbell shape to it, okay, like this. So remember I said they're going to fill into their orbital. The S only has one orbital, so it's a sphere. And they will pair right there, both of those electrons. They'll pair together and they'll orbit this sphere. Okay? When you jump into the P, there are 3 orbitals, right? There's 6 electrons. That means there's 3 orbitals. So when I jump into the P, I have 1, 2, 3 orbitals. Those orbitals are not just a sphere. They're more of this dumbbell shape, they call it. And you can see they're in these different planes, X, Y, and Z planes. Okay? So you have all 3 of those on top of each other in those different planes. And you'll first put one here, and one here. And then you'll come back and pair 1, 2, 3. So you'll have 6 total electrons in each of those 3 orbitals. Okay? 2 electrons in each orbital, a total of 6 electrons with 3 orbitals. That's the P. So you have an S, and then you have the P's, and then the D's. I don't know if they show it. Do they show it? They don't show it because it's way crazier. It's way crazier. The D's are just a mess, and the F's are just like really crazy. Okay? But that's the idea with those orbitals. That's how those orbitals are used. Okay? All right. How many electrons can be in the 4D subshell? 10, right? You can have 10 electrons, 5 orbitals, 10 electrons. They will first individually fill those orbitals, 1, 2, 3, 4, 5, and then they come back in pair 1, 6, 7, 8, 9, 10, until all the orbitals are full, and there are no unpaired electrons. Okay, so the electron configuration is going to determine where the electrons are in those orbitals. Okay, there are a few principles that we follow when we're writing electron orbital diagrams. Electron orbital diagrams are diagrams that represent the energies of these orbitals and where the electrons are. Okay, so one of those first principles is that electrons fill in the lowest energy orbital that is available. That's what we're just talking about, right? And that's shown here on the periodic table. If you see your periodic table, you can see where the lower energy is. 4s is lower in energy than the 3d. Okay? 6s is lower in energy than what?
3D.
Not 3d, but 3, 4, 5d. What's lower in energy than the 5d? What's between the 6s and the 5d? What's between those? What's higher than energy? What's higher in energy than 6s and lower in energy than the 5d? 4f. Look at the numbering. 56. Where's 57? In the f's. 71. Where's 72? In the 5d. You have to follow the numbering. 6s, 4f, 5d. That's how that fills. 6s, 4f, 5d. What's after 5d? Here, this is where it is, where I am. What's this? 6p. 6p. How can I be sure? Because I know what the first element of each group is labeled as. Hydrogen, what would I label it as? 1s. Boron, number 5, what would I label it as? Not 1p, 2p. Scandium, number 21, what would I label it as? 3d. That's the most tricky one. That's the one that everybody is tricked by. It's not 4d, it is 3d. Down here, number 57, what am I going to label it as?
5F.
Not 5f. 4f. Now, this is how you know. This is how you know. All you have to do is count to 4. 1, 2, 3, 4. 1, 2, 3, 4. That's all I have to be able to do. 1, 2, 3, 4. Then I know the first element of each group starts with either 1, 2, 3, or 4 in order. 1, 2, 3, 4. Now I know exactly where I am. And I just have to count down. 3, 4, 5, 6, 4, 5. 2, 3, 4, 5, 6. Okay? I'll know exactly where I am because I know where I'm starting. 1, 2, 3, 4, S, P, D, F. 1s, 2p, 3d, 4f. Those are the first elements of each group. 1s, 2p, 3d, 4f. Okay? That will keep you straight. So, for those of you who have learned some weird, going back and forth method of doing electron configurations, forget it. It's a mess. Okay? And it's so much easier to just look at your periodic table and be able to read it. If you understand your periodic table and you can read it, you will be able to write electron configurations with no trouble at all because it'll be so intuitive. 4s, 3d, 4p. Okay? I will be able to read it. Okay. Oh, did I talk about this rule? Electrons fill the lowest energy level orbital. That is available first. Yes. Okay, so we know that. Okay. Exclusion principle. Pauli exclusion principle. Each orbital can hold up to 2 electrons. Right? We know that. But their spins are in opposite directions. So if I was showing the spin of an electron, so let's talk about boron, carbon, nitrogen, oxygen, fluorine, neon. There's 3 orbitals there, right? 3 orbitals. And this is how I represent it with little dashes here. And I'd say boron has 1 electron and is spinning in the up direction. Boron, carbon, nitrogen. They fill in the 3 orbitals first, up, up, up. They're all spinning in the up direction. How can I pair an electron with something that's also negatively charged? An electron with an electron. Does that make sense? Shove 2 electrons together. Their opposites have to attract, so 2 negative charges don't attract, right? How am I going to get those into the same orbital if they're the same thing? How are they going to pair? You've got to spin it in the other direction. You've got to create magnetism in the other way. Just like on a wire, electrical charge. Okay? If you have can create magnetism with electrons flowing one way, will be paramagnetic to electrons flowing another way. So you spin them in the opposite direction. And now they can pair. Okay? Now those electrons can pair. And they fill those orbitals. So that's what this exclusion principle is. You fill them first up, 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 and then you fill them down, down, down. Okay? So if I had 3 orbitals and I went like this, and I said that's for nitrogen. Up, down, up. That's wrong. Okay? This is incorrect. It needs to be up, 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 then down, down, down. That's how they will fill. Okay? In their electron orbital. Whoops, one other rule. Each orbital in a subshell is half filled. Okay, we already talked about it. Before it becomes completely filled. All right? So that kind of follows the same. So here's 1s, 1. That's hydrogen's electron. Okay? And if I was going to put helium's in there, I would put it in the down spin to get 1s2. Okay? 2 electrons there. Do not do that. Please, please, please. It's such a mess. I mean, you're trying to memorize something, which you don't need to. You just need to, you're going to have your periodic table. It's going to be right in front of you. And if you label it, you walk into class, you label it. Well, I guess it's probably going to be like a computer. But if you understand it, 1, 2, 3, 4, you're okay. 1, 2, 3, 4, 1s, 2p, 3d, 4p, 4f, excuse me. I will know where everything is. Okay? And I won't have to try to learn this big mess of going forwards and backwards, okay, to fill my electrons. I'll just simply read my periodic table, and we'll practice it. Okay, the S sublevel has 1 orbital. The P sublevel has 3. The D has 5. Okay, I think we're okay with that. Here are some orbital diagrams of hydrogen, lithium, 1s up, down. 2s has 1 up for lithium. Okay? All right. So we're going to write some electron configurations here for these elements. Okay? And the orbital diagrams we're not really going to work with a lot. More it's this, what we're going to do here. Writing the electron configuration. So beryllium, I want to write its electron configuration. I'm going to start at hydrogen. Hydrogen is found in the 1s. Okay? Helium is also found where? 1s. So the helium is a little bit deceptive in its position, right? It is not actually right here. it has 2 valence electrons. It's actually right there next to hydrogen. It's in the s orbital. Why do they put it over here? Because it's a noble gas. It's inert. It's non-reactive. It has a full valence shell. Okay, that's why. So helium is also in the 1s. Okay, so to get to beryllium, I start in the 1s. What comes after the 1s? Read your periodic table. What comes after helium? Lithium and beryllium, which are in the 2s. Now, what is the position of beryllium in the 2s? 2s2. So, I first write out all of the principal and subenergy levels that I have. And then the very last element, I write its actual position, where it resides. Here, beryllium is 2s2, and then I'll go back and I'll fill everything in. All s's hold how many electrons? 2. 1s2, 2s2 is the electron configuration of beryllium. Nitrogen. We're going to start nitrogen out with the exact same electron configuration as beryllium because it comes after beryllium, right? 1s2, 2s2. Now where do I go? 2p. What is nitrogen's position in the 2p? 3. That's the electron configuration of nitrogen. 1s2, 2s2, 2p, 3. Sodium. Okay. 1s, 2s. What's after 2s? 2p. 2s, 2p, 3s. Sodium is which element in the 3s? That's right. 3s1, and then I fill everything in after before it. 6, 2, 2. 1s2, 2s2, 2p6, 3s1. That is the electron configuration of sodium. Chlorine. Once again, start back at hydrogen. 1s. Lithium, 2s. Then I jump over here to boron's group. 2p. Then I go to sodium's group. 3s. Then I come here. 3p. Chlorine is what position in the 3p? 5. I fill everything else in. 2, 6, 2, 2. 1s2, 2s2, 2p6, 3s2, 3p, 5. Okay. All right, let's go to silver. Okay, so silver, I'm going to start in 1s, then to 2s, and then to 2p, back to 3s, over here to 3p. Whoops. Where do I go after the 3p? Potassium, 4s. Whoops. Now where? Now to the 3d. That's the toughest one. But you guys, you know what this is because we've talked about it. This is the third D. Okay? So 4s, 3d. Now where? 4p, 3d. This is the 4. And if I'm not sure, what do I do? 2, 3, 4p. This is 4p. After the 4p, where do I go? 5s. Now where? 4d. What is silver's position, Ag, in the 4d? 4d9. There's 10 of them, so I subtract 1, 4d9. Okay? So this is, so I go back and I fill everything in. All S's have 2, P has 6, D has 10, 2, 6, 2, 6, 2, 2. the electron configuration of silver is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. That's its location, 4d9. Okay, so we can easily see that here now, right? The S's, the P's, the D's, and the F's, all in their groups. And we just simply, we can just simply write them out. 1s, 2s, 2p. We're just following our periodic table. 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Now where? 4f. 6s, 4f. 56, 57. 6s, 4f, 5d, 6p, 7s, 5f. Excellent. 60, 7p. That's as far as we can go. They're not showing anything in the 7p, but there are elements there now. They've actually created them, discovered them, okay, synthesized them. So they have now, this is an outdated periodic table, I guess, because we now know those elements, okay? That's a very recent thing, just in the last 6 months or so, they found those. Okay, shorthand electron configuration. You can imagine if you want to write the electron configuration of mercury, number 80, you're not going to want to start at hydrogen, even though on your homework you're going to have to. Well, I don't know. Actually, I gave you guys Connect homework now, so I don't know. In my homeworks that I had before, you would have to. But you might have to. Just realize that, okay? Still, there's a quicker way, okay? That's acceptable. And the shorthand configuration is to go to the closest noble gas. What is that falling behind, not forward, but backwards? Okay, that's right, xenon. So we would say Xe, and we would know that the electron configuration of everything before that is full. Everything is full. We start with Xe. And then where would we go? 6s. And after 6s, 4f. And after 4f, 5d. And what is mercury's position in the 5d? 10. And then I fill everything up before it, 14, 2. So, the electron configuration of mercury is xenon, 6s2, 4f14, 5d10. That is its shorthand electron configuration. That's how I'd write it in shorthand. Okay. So let's write the shorthand electron configuration of these examples. Nitrogen. Where am I starting? He. Brackets, He. This one's kind of worthless to write in shorthand, but go ahead and do it. 2s2. Good. 2p3. That's nitrogen. Sulfur. Ne. Then what? 3s2. 3p4. It's fourth element in the p. In the 3p. Okay? For sulfur, right here. Okay? Titanium. Argon. 4s2. 3d2. Titanium, number 22, is in the second position of the 3d. Okay? Tin, Sn. Tin. Good. 5p2. That's its position. 5p2. Okay? See, once you understand how the periodic table works, how it's put together, writing an electron configuration is simply the process of reading your periodic table. The easiest thing that you could do. As long as you understand it. As long as I understand how this is set up, I can easily write an electron configuration for anything on here. Okay? Can easily do that. Okay. Valence electrons, outside electrons, noble gases are stable. Okay? They're inert. They don't react. And it's due to the fact that they have a valence shell of S and P electrons that are full. Okay? And that brings us to that octet rule. This is the octet rule that everybody basically wants to get here. They want to get to this stability that they have. They want to have 8 valence electrons. So they're going to lose or gain electrons to do that. So everything other than the noble gases, basically as you move away from them, you're becoming more reactive. So that because you want to gain that stability. Okay. And you're going to do it by losing or gaining electrons. And when you lose or gain electrons, you become charged. If I lose electrons, am I going to become positively or negatively charged? Positively charged. Why? I have less electrons, which are negatively charged. And what do I have more of? Protons. Not that I gained protons. I don't want to confuse you. I didn't gain protons. I just have more protons than I do electrons. Because before I lost an electron, I had the exact same number of electrons as protons, and my atom was neutral. It was at a 0 charge. But if I lose an electron, that unbalances the electrons and the protons, and there's more protons than electrons, and so therefore I have a positive charge. So if I gain electrons, what charge do I have? A negative charge. So if I add electrons, I'm negatively charged. So a plus is a negative, and a negative is a plus. That's how it works. It's all confusing, right? Okay, well, that's how chemistry is, guys. It's all backwards the whole time. It's just like that, okay? So if you're dyslexic, you're going to do wonderfully, all right? But otherwise, you're just going to have to figure it out. Plus, negative, negative is plus, okay? If I gain electrons, they're negatively charged. That means I have a negative charge on my element. Which of these elements on the periodic table are going to gain electrons?
The P's.
These ones, the P's, the non-metals, right? Are they going to be negatively charged or positively charged? Negatively charged. If I am nitrogen, what charge am I going to have?
Negative charge. 3.
That's right, a negative 3 charge. Because how many electrons do I gain if I'm nitrogen? 3. What if I'm oxygen? What's my charge? Negative 2. Do you see how your periodic table is your friend? It tells you how many electrons and the charge of this when it becomes an ion. Negative 3. Negative 2. Negative 1. Negative 1. Negative 1. Negative 1. Negative 2. Negative 2. Negative 3. Negative 3. Okay? It tells me the charge. I can predict it from there. Magnesium. What charge is it going to have? Number 12. Positive 2. It's going to lose 2 electrons. Okay? So here you can see the example of sodium. Sodium, number 11, has 1 valence electron. It wants to have 8, like neon. So it loses an electron and becomes like neon. Well, what caused it to lose that electron? It just doesn't spontaneously lose it. Something has to force it off of it. But it will give it away if something is pulling at it. Well, in the presence of fluorine, who wants 1 electron, sodium in the presence of fluorine will pull that electron off of sodium. Sodium will happily give it away to him. So fluorine accepts it and becomes negatively charged. Sodium becomes positively charged. Now I have 2 ions. Ions are electrically charged particles. So I now have these 2 ions, a positive ion, a negative ion. What are they going to do? They're going to come together. They're going to find each other, right? So sodium loses an electron. Okay, fluorine gains it, and you'll form sodium fluoride as the result of that, okay? That's an ionic compound because it forms by ions. Ions are charged particles, and they form ionic compounds. Oxygen, like we said, is going to gain 2 electrons, become O2 minus. Aluminum. It's a metal. It has 3 electrons, 3 valence electrons. It will lose them and become Al3+. Now, I can predict this one, but I cannot predict this one. Why? Because what's in front of this guy? The D's. The D metals. And I cannot predict how many electrons it's going to lose. It will lose electrons, but whether it loses 1, 2, or 3, I can't predict, because these guys I can't predict either. D metals are unpredictable in how many electrons they're going to lose. They could lose 2, they could lose 3. You can have iron 2, you can have iron 3, you can have iron 1. Those are all real elements, okay? And it's unpredictable, okay? So once I get into the D's or past it, I cannot predict the charge, except for 3 exceptions. Zinc, cadmium, and silver. 2+, 2+, plus 1. Those are the only 3. Other than that, I don't predict the charges of these guys because they're all over the place. All right? These ones, yes. These nonmetals right here, yes. Okay? Those are my representative elements. I can use them. I can predict those charges. Okay? All right, we'll talk more about that next time.